Good morning, good afternoon. I'm glad to be here to share some of our work on the software stack. It's actually mainly this system software. So what I mean by this system software is that we would like to build the software infrastructure such that we can help the developers to better reach the underneath hardware device. So there are several parts I would like to go over, but I don't have to go over all of them. So feel free to ask me questions at any time, and then we can have some discussion. So first part, I'm going to talk about quantum assertions. So let's see why do we need these quantum assertion and what they are. Okay, so far I would say I'm not sure what do you guys feel about this summer school and workshop. So my feeling is that it seems that the Institute has done a really fantastic job of bringing in all these smart people, because the material, to me, is really hard, okay? So as a result, what I'm thinking is, okay, when I try to write code to implement those algorithms or protocols, so what I get, I will probably spend a lot of time debugging, right? So that's also the same thing that other people have discovered as well. So there are a lot of bug reports, and due to the complexity of the underneath math and the quantum behavior, I believe that this debugging issue would be as difficult as we have observed in classical computing, right? So as an example, in this bug report, you can see that there are some bugs being reported, and over there is actually just the face has been applied in the wrong way. So that would lead to obviously incorrect output results. Okay, so let me tell you a little bit about this assertion work in terms of several works leading to this direction. So first one, in 2019, a group at Princeton University, they proposed to use assertions to help the debugging process. So over there on your right-hand side, you can see the highlighted kind of assertion type of statement. So over there they say, okay, you have this assertion to check some quantum variable. So in this particular statement, it's checking whether this quantum variable is a classical variable or not. It basically means when you marry it, you should get some classical value. And the parameter over there is like the first one is the variable name, the second parameter is the data width, and the third parameter is expected constant value for that particular quantum variable. So that's basically what being proposed by this group to say that these assertions can help, just like the assertions in the classical programs, can help to pinpoint where the program execution can go wrong. And in order to achieve those assertion statement, meaning like in this particular case, we want to check this variable, this quantum variable or these qubits should be in the classical state. So how do we achieve that is they propose at the time to use this statistical approach. So what it means by that is we basically need to, for those qubits of our interest, we need to measure them directly at the computational basis. And in their paper, they talk about several different types of assertions that turn out to be useful in identifying or helping developers to find the possible bugs in the program. But this type of statistical assertion has their problems. One obvious limitation is that when you perform this measurement, we have to stop the program execution. So as a result, these assertions become like breakpoints during program execution. So when you do a measurement, you have to stop. And then next time you also need to stop again to do another measurement. Because this is a statistical approach, we need to repeat this measurement multiple times and run some sort of a statistical tests in order to establish some statistical significance of our results. So that's the kind of the first work on that direction. And later on, we say that, okay, in general, what we want to support in terms of assertion is something like this kind of assertion statement. So the semantics would be, we have some quantum state under test, and we have some quantum state as expected. We want to check whether the quantum state under test is the same or is the same as the expected state. So that's kind of like the semantics of this assertion statement. And also what we want to support is that this expected state better to be general, not just to say it's a classical or it's some very special superposition or the entanglement state. So toward that way, like one early work in 2020 is basically say, okay, we can propose, we can build some simple circuits that can assert some very specific states. So over there we have some like assertion circuits for classical values and uniform superposition, so on and so forth. So as you can see, probably can recognize some of these very simple, just like stabilizers on some directions. So what I'm going to talk about actually in this work is we want to show you guys some systematic ways to build these assertion circuits such that we can support asserting all these kind of different quantum states. So we besides this what we call like this equal state, that's what we mean by.
Sorry, so Blint, are you seeing the presenter mode?
Just showing the first slide.
Oh, is it showing that screen up there?
Yeah. How's that better?
No, it's not.
Yes.
Oh, no, it's good.
Because it's.
That is good.
Okay, yeah, good, right. All right, okay. So what I was saying is that in our work, besides this, what we call as a precise assertion, which means we check the quantum state, whether it's the same as expected state or not, we also propose something like a membership check, meaning that we gave the expected state rather than a very precise description using either a vector or the density matrix. What we have is we gave a set of states such that as long as the state under test belongs to that set, then we will say, okay, this would be a assertion that would pass. And otherwise, if the state under test does not belong into the set, we will raise an assertion error. Okay, so that's what we call as an approximate assertion, rather than the previous one we just compare the two states in an exact manner. To illustrate a little bit about this approximate assertion. So for example, in some algorithms or in some circuits, we don't really know, or as a developer, we don't really know the exact output or at a certain program execution point, what that quantum state would be. So as an example, this Deutsch-Jones algorithm. So in this algorithm, we have this black box function. So as a programmer, we write that black box function, and the functionality of that black box function is to either produce a constant output or it's a balanced output. But think about the case that I have some bug in my code to model that function, but my output is neither a constant, and also is not a balanced state. So how can I capture that bug? So that's where we say, okay, this approximate assertion could be helpful as long as we can check the state that output from that black box, whether it belongs to that set of balanced state and constant state. So that's what we consider as the usefulness about this approximate assertion. So this approximate assertion and precise assertion also present an interesting trade-off in terms of the assertion circuit cost and the assertion checking accuracy. So as an example, we say, okay, considering this GHZ state. So let's see, okay, this is a fairly straightforward protocol or the circuit to build this GHZ state. So if you look at, we have different type of assertions to check this state. So we can use this precise 3-qubit state as the expected state, such that we can check the output to see whether the output state is the same as this expected state. And also we can say, okay, rather than checking all these 3 qubits, how about we only check part of it? Part of it, when you only check, like, for example, in this case, 2-qubit state, it becomes a mixed state. So we can check whether this mixed state fits our expectation or not. Or in other words, if we use this approximate assertion, we can check just like this membership to see, okay, whether the output state belongs to this set of all zeros and all one state. Okay, so if you think about the code that we can write to build this GHZ state, so it's kind of like the code showing up on the right top hand side. And if you think about the case with this simple bug, which basically means we somehow alternate the statement of the last two, right? So in this case, the output state will be generated is highlighted over there. And from that one, obviously, as you can see, either we can compare exactly this 3-qubit state to capture something goes wrong, or we can use like this checking this membership, because membership checking make sure that the output state belongs to this 000 or this 111 state. So once you have this component of 011 state, it would raise an assertion error. Okay, but in this particular case, if you only check the last 2-qubit state, it would not be able to catch this particular bug. As another example, you see, okay, for the same protocol, if I somehow, change the order in my first statement, the parameter order is altered. So as a result, I will have a phase error in my output state. So in this particular case, only that 3-qubit precise assertion would be able to catch this particular bug, and that membership will fail because it does not check the phase information. It only checks the membership of whether the output state belongs to that set or not. It does not have that phase information being encoded. So now let's look at how we build this assertion circuit such that we can support this checking of this precise assertion. So we proposed 2 different ways. So over here, I will just talk about one of them because hopefully it's raised some bells in terms of stabilizer, as you will see. It's relatively straightforward, hopefully. So this stabilizer, or this what we call like this non-destructive discrimination protocol. So it all relies on this particular circuit. We have this Hadamard gate, and then after that we have a controlled U gate, and then followed by another Hadamard gate. So when you have this stabilizer structure or this NDD type of circuit structure, if the input goes to that controlled U gate, if that the input state is the eigenstate of that control U gate with the eigenvalue of 1, if you have that, then when you measure the qubit showing at the bottom of that figure, when you measure that qubit, you will get the result of 0, or because the eigenvalue is positive 1. And if otherwise, if the input state is the eigenstate with the eigenvalue of -1, then we will measure the result as -1. So we are going to take advantage of this particular circuit to construct this assertion check circuit. So the way, the goal is to achieve this, compare these 2 states. So the first state is the state under measurement, or not under measurement, is under the check. And the second state is our expected state. So our goal is to build this controlled U gate such that when these two states are different, it will raise an assertion error. If these two states are the same, then we will not raise an assertion error. So in this case, raising an assertion error means our measurement outcome would be 0. So the way we do that is we can construct this controlled U-gate in the following manner. So starting from this expected state, presented over there as state mu, so we can build an also normal basis with mu, for example, being put as this psi sub 0. And then based on this also normal basis, we can construct this unitary matrix U as showing over there. So that one, as you can see, when we construct it using that equation, this state mu would be the eigenstate of that unitary matrix U, and the eigenvalue is 1. And for all the rest eigenvalues, for all the rest eigenstates, the eigenvalue would be -1. So that's the way we construct this controlled U-gate such that it can check the expected state to say, okay, if the state under test is not the same as the expected state, it will raise an error. Otherwise, it will not. Okay. So this circuit also has the benefit in terms of some sort of error correction or error mitigation, because even let's see in the scenario when the state under test, include both component of the correct state and some component of incorrect state. But when you perform the measurement, if the measurement outcome is indeed 0, it basically this projective measurement would force this input state to fall back into your expected state, because all these incorrect state will be basically eliminated, right? So that's basically some benefit of using this assertion circuit as a lightweight way to achieve some sort of error mitigation. So this basically is this one way of building our assertion circuit. And when we think about kind of more complex scenario with mixed state or this approximate assertion, meaning that we want to check multiple states at the same time. So it's actually, the process is similar. The only difference is that rather than a single correct state, we will have multiple correct states. And then, all the rest process would be, built in a similar manner. So as an example to illustrate actually, building this, funding this also normal basis, and also funding this unitary matrix U, sometimes is actually quite trivial. So as an example showing over there is that, for example, we want to check this membership, we want to say, okay, this is an approximate assert. So we want to check whether the input state or whether the state under test belongs to this set of 0, 0, or 1, 1. So the way to do that is, okay, we can, because the correct state is 0, 0, or 1, 1, and then we can construct this orthonormal basis really in a straightforward manner. So the orthonormal basis would be 0, 0, 0, 1, so on and so forth. So that's our orthonormal basis in a trivial manner. And then we can construct this unitary matrix by saying, okay, this would be, Kidbra 0, 0, and then 1, 1, 0, 1, 1, 0. So with their corresponding sign to represent their eigenvalue. So we can build that unitary matrix U, and it turns out to be just these, these poly Z operators. And then the circuit design showing up over there would be, okay, that's just a standard stabilizer check for those, poly errors. So that's basically, the assertion error checking logic that we propose. And some examples to illustrate this, the way of using this assertion circuit. One is this quantum phase estimation. for this quantum phase estimation for small circuit, we can know exactly at each point what would be the state during execution. So if we know all these state, so what we can do is we can use all these assertions at different points of the program, so that it kind of give us the illusion of stepwise execution. So basically, you can, just like when we debug our classical program, we sometimes step through the execution, right, to see, okay, what is going on after each step, what is the execution outcome at that point. So this one, as long as for these small programs, we can have this kind of capability to check that. And also for large programs, for large quantum programs with high number of qubits, this obviously get out of control. So over there, what the challenge would be, we needed to identify those program or these result invariants. So in this particular case, for example, in this phase estimation, when you look at the input qubit state at the bottom, so that one, because it goes through all these, this U gate for this state psi being its eigenstate, so that just state will not change after each gate. So you can use that one as the invariant to check whether my program behaves in a reasonable manner or not. And also you can use that simple check, as I mentioned before, to kind of perform some sort of error checking to see whether your hardware error has corrupted your output state. So over there, we actually did some experiment showing that using that simple approach, it can indeed improve the success rate of that type of circuit. The main reason is because the assertion circuit complexity is much smaller compared to your original circuit complexity. So if your original circuit is simple enough, then that sort of error mitigation technique typically will not work too well. So that is one example. So another example, as we mentioned before, is this Huiyang Zhou algorithm. So in order to check this constant or this balanced state, so what we can do is we can list all these balanced state as well as a constant state, such that we can perform this membership check. Okay. So that's kind of like two examples to illustrate this. So the takeaway message is that the quantum programming is challenging, and we expect that bugs will be around. And we propose this assertion as a primitive to help developers to debug the program, and also these assertion circuits can serve as an option to help us to mitigate the hardware errors. So that's basically the takeaway message of this part. So any questions? Yes.
Two questions. So one is when you run this, would you know you have a kind of a bug in your program, or your hardware is imperfect?
Okay, so yeah, the question is when I run the program, with those assertions, when there is an assertion error, how do I know whether this is a result of a hardware error or is a result of a program bug? So in that case, yeah, indeed, we don't know. So under the debugging part, we pretty much rely on like noise-free simulators, such that when you perform this testing, you know that the noise will not interfere with your software bug. But otherwise, indeed, this is not distinguishable under the current protocol.
Maybe a sort of related question. I mean, if you're just debugging the code, it would be much better if you could find a way to debug it without actually needing a quantum computer. So can it be done classically?
Yeah, debugging code without running on the that would either you rely on the classical emulator, or I think that is possible. But what we want to say is sometimes we also want to check whether the hardware gave you the faithful implementation of a gate or not. But I think that's a good point. Yeah, with classical simulators, you can always check what is going on after each step. Yes?
What is the largest number of qubits for which you expect to be able to construct U? Because it looks like a highly non-local and complex operator in general.
Yeah, that's the question is how large, what is the limit in terms of number of qubits or the dimension of that control U gate that we can construct? That is indeed a good question. So far we tried like, a small number of qubits for the reason as you mentioned, and but there are like a progress being made on this gate synthesis, such that you can take a large unitary matrix, you can generate or decompose it into a next set of quantum gates, but it's kind of like a different direction of research. Yeah.
Okay. It looks like sometimes designing these assertion checks is just as hard as designing the circuit itself. Could it be the case?
Okay, so the question or the comment is that sometimes when you design this control U gate, the complexity is almost the same, or maybe sometimes even more complex compared to your original circuit. So that is, sometimes is indeed the case. The argument over there is that once you have different ways to build this, expected state, because you have different implementation. So hopefully, if one path is wrong, the other path will be able to detect it. Okay. So if no other questions, let me quickly go to my second part, and probably we can start quickly over there. Okay, so second part of our system software support is actually about this transpiler. So actually some step in the transpilation process. So let me give you a quick overview of this transpilation process. So when I use a develop a quantum program, the underneath hardware, the assumption for this underneath hardware is that this hardware can support, or this quantum device can support all kinds of quantum gates, and also all these qubits would have all-to-all connection. Because when we write programs, we do not want to consider the specifics of your target device. Otherwise, if you change your target device, you have to rewrite your code. So that would not, give you a very good productivity. So as a result, when we write the quantum program, the transpiler for a particular target hardware device needed to do some work. So the first step is typically to say, okay, I need to map your arbitrary quantum gate into a set of native gates that the quantum device can support. So typically that's what we have over there, as we see, in this example. For example, over there, we have a Toffoli gate, and Toffoli gate, if it's not supported natively, it will be decomposed into a series of single or double qubit gates. And after that, we also have this assumption of all-to-all connection, which for many technologies would not be the reality. So as a result, we need to perform qubit mapping and qubit routing. So following this example, let's see, okay, we have this linear device layout, or the coupling topology is just like showing over there. You have 3 qubits, and there is coupling between the first 2 and the coupling between the second 2. But there is no connection between the first qubit and the third qubit. So as a result, when you want to perform a quantum gate between the first and the third qubit, so we have to insert some additional gates. And the typical way is to insert swap gates such that the state can be get close to each other, and then they can perform the required gates. Right? So that's the step called qubit mapping and qubit routing. And sometimes this step is also referred to as a quantum synthesis. And after that, after this, mapping to the native quantum gates, as well as the mapping and routing process, the resulting circuit will go through some optimization process, such that we can perform gate cancellation and some other additional optimizations. And after that, we will perform, all these transpiler will perform scheduling to achieve some, or to optimize some objectives. So for example, in this particular case, if we want to, the goal is to reduce crosstalk errors, we may, kind of like shift 2 concurrent gates slightly apart, such that the crosstalk effect can be minimized. So that's the overall process, the typical process of this transpilation. So our work mainly focus on this qubit mapping and routing step. So our motivation is essentially like in the current qubit routing algorithms, as we mentioned in the previous slide. So we do this qubit routing, and after that we perform this circuit optimization. So as a result, these qubit routing decisions are made without knowing the subsequent steps of optimization. So that would lead to suboptimal decisions in terms of qubit routing. So as an example, I show in this slide. So assuming that we still have this linear topology, so 3 qubits connected in the linear manner, and in order to support the controlled U gate number 3, so that's a U3 qubit gate, because they are not, these 2 qubits are not physically connected to each other. So we need to insert swaps. So in this case, we have 2 options. We can either insert a swap between the last 2 qubits, or we can insert a swap between the first 2 qubits. So as shown on the top of this slide, when you insert the swap gate between the last 2 qubits, because these swap gate cannot be, or these resulting 3 CNOTs cannot be combined with any other neighboring qubits, neighboring quantum gates. So as a result, we have these 3 extra CNOTs being required to support this swap. And if you look at the decision at the bottom, because it's, there is this controlled U2 gate before the swap gate, so you can perform this gate optimization such that this swap gate does not require 3 CNOTs. It only requires 1 in this particular example. So the motivation behind this is that different routing decisions, if you consider the subsequent optimization opportunity, they actually have different costs. But the current approach in terms of qubit routing, either you use heuristic approaches or you use some optimal solvers, we always consider, all these previous approaches, they always consider using the number of swaps as the cost function to say, okay, either depending on how many swaps you need to insert, then you decide which option you want to take. So our approach saying that we really should not use the number of swaps as the metric. Instead, we should consider things like the number of CNOTs that is required when you consider the impact of subsequent optimization processes. So that's kind of like the takeaway message. And just some kind of quick numbers to illustrate the impact from IBM Qiskit. So as you can see over there, after the routing step, some statistics to show many of those swaps can be optimized. So meaning that there is a lot of opportunity for this subsequent optimization process to reduce the actual cost of these swaps. So that's basically served as our justification to say, rather than considering this number of swaps as the mean metric to make our decisions on qubit routing, we should use the number of CNOTs after we consider the impact of the subsequent optimization processes. Okay, so I think with that, probably I'll go to some quick results, and then I will just stop writing. Okay. Okay, so as I said, this is our approach that not all swaps have the same cost. Hopefully, I made a case for that argument, and we propose these heuristic solutions, and we also consider different type of optimization opportunities in the subsequent optimization phase. The overall result actually shows some statistics to show that our results, kind of quite effective. reduce the number of the circuit depth after routing. And in terms of compilation time, it also does not increase too much in terms of compilation for large circuit. The main reason is that once we eliminate those gates, and actually it would benefit the subsequent transpilation processes. So that's why, the overall, although we spend more time on qubit routing, but the subsequent compilation passes will take a less amount of time. So that's basically, the takeaway message. So any questions at this point? Yes, please.
So, 2 slides back, you mentioned 2 observation techniques, the gate resynthesis and the swap.
Yeah.
How long do the observation functions take?
How long? The question is about the transpilation time or transpilation latency of these optimization processes. On top of my head, it's fairly quick, but it also depends on your input circuit complexity. Yeah, for our cases, it's not very complex, and also the argument is that nevertheless, the transpilation will go through this process, anyway. So yeah, we simply change the location where this functions is being invoked. And then after being invoked this, we take record of which gate can be optimized. Yes?
So there's another work that you where they perform swap absorption.
Yeah.
In combination with optimal solver implemented compilation. I wonder, how does your heuristic compare?
Yeah, the question is about a previous work which uses swap absorption such that when they make decision in terms of qubit routing, it considers the opportunity of the inserted swaps can be canceled out with the neighboring quantum gates, right? So our work shows that when you look at the optimization opportunities, the inserted swap sometimes, and actually quite often, it is not either you can absorb it or you cannot absorb it completely. It's somewhere in between. It's like, in the previous work, it just say, okay, if you can absorb it, so the swap number, you reduce by 1, right? If you cannot absorb it, you keep the original number of swap gates. So in our case, our argument is that you should consider the number of CNOTs rather than the number of swaps, because sometimes when you insert a swap, you need 3 CNOTs, sometimes you need 2, sometimes you need 1, sometimes you need 0. So in the previous work, you can consider as they can only think about the swap, the cost is either 0 or 3. But actually, they are quite often, it shows somewhere in between. It's 1 CNOT or 2 CNOT rather than 0 or 3.
Possible equivalent transform. For example, you can commute signal further down and merge with other signal elsewhere.
Yeah, that's the comment was if we consider, if I interpret your question correctly, the comment was if we convert these heuristics into some sort of constraints in an optimal solver, will it lead to better results? Things like that. Yeah, it is actually quite possible. So the only thing is that, it's some kind of scalability of those optimal solvers. But nevertheless, I totally agree that when we convert these constraints in the optimal solver, I think we should get better results than our heuristic-based approach. Okay, any other comments, questions? Thank you.